Imagine standing in front of a conveyor belt. It's moving at 2 meters per second. Hundreds of clear plastic water bottles are whizzing past you. Your job? Spot the one bottle in 1,000 that has a hairline scratch or a tiny crack near the cap. You might catch the first one, maybe the second. But after 10 minutes, your eyes glaze over. You start blinking. And that's when a defective unit slips through, leaks onto a pallet, and costs the company thousands in returns and damages. This is the reality of industrial quality control. Humans are brilliant, but we aren't built for repetitive, high-speed attention. Machines are. Today, I'm going to take you through the entire journey of how I build a computer vision anomaly detector from scratch to solve this problem. We aren't just going to look at the code. We're going to deconstruct the architecture of the neural network, understand the mathematics of how it learns, and look at the data engineering required to make it production ready. I had to experiment with different architectures, fight against memory constraints, and figure out how to train a model when I barely had any data to work with. Let's start where every machine learning project actually begins, the data pipeline. I started with a raw scrape of bottle images, and immediately I hit a wall. Real-world data is messy. I had images of all different aspect ratios, resolutions, and file formats. But the biggest issue was transparency. Many of the images were PNGs with transparent backgrounds. In computer vision, an image is just a matrix of numbers. A standard image has 3 channels: red, green, and blue. But a transparent PNG has a 4th channel, alpha. If you feed an alpha channel into a standard neural network designed for RGB, the math breaks down. Even worse, if you just drop the alpha channel, the transparent areas turn black. To the computer, that looks like the bottle is floating in a void, which confuses the edge detection layers. I wrote a script called image_reshape_and_reformat.py to handle this. I used the pillow library to check the image mode. If it detects RGBA, it creates a new white canvas, pure 255, 255, 255, and pastes the bottle on top using the alpha channel as a mask. This flattens the image into a standard 3-channel RGB format with a clean white background. Then came the question of resolution. Originally, I resized everything to 500 by 500 pixels. My logic was simple. Defects are small, so I need high resolution to see them. This turned out to be a trap. When I tried to train the model, 500 pixel images consumed so much VRM that I could only fit a tiny batch of images onto the GPU at once. This made the training signal unstable. I eventually realized that a convolutional neural network is much better at feature extraction than a human eye. I added a transform step to resize everything down to 150 by 150 pixels. It sounded counterintuitive to shrink the image to find small defects, but as we'll see, the network's filters are robust enough to handle it, and the training speed increased by 400%. But fixing the image format was the easy part. The hard part was the class imbalance. In a factory, you might produce 10,000 good bottles for every one bad bottle. If I train a model on that data, it would just guess good every single time and achieve 99.99% accuracy. And it would be useless. I needed more defective data, and I didn't have the budget to go buy thousands of bottles and break them myself. I solved this 2 ways. First, geometric augmentation. I wrote a script called rotation_images.py. It loops through every image I have and creates 5 new variations. I use a random uniform distribution to pick an angle between 30 and 330 degrees. The key here was using bicubic resampling. When you rotate a grid of pixels, the new pixels don't line up perfectly with the old ones. If you use cheap interpolation, you get jagged edges, aliasing. To a neural network, jagged edges look like cracks. Bicubic resampling smooths those transitions so the model doesn't learn fake defects. This multiplied my dataset by 6 and taught the model rotational invariance, meaning a scratch is a scratch, whether it's vertical, horizontal, or diagonal. Second, and this was the fun part, synthetic defect injection. I wrote a generator called generate_defects.py. The goal was to take a perfect bottle and mathematically scar it. But I couldn't just draw random lines on the image. If I drew a line on the white background, the model would learn that defects float in the air. I needed the defects on the bottle. I implemented a function called detect_foreground. It uses number py to subtract the background color from every pixel. Where the difference is high, that's the bottle. I capture those coordinates. Then, I wrote functions to mimic real, physical damage. Add_square picks a random spot on the bottle and uses OpenCV to draw lines of varying thickness and darkness. Add_include simulates dirt or a label error by drawing a solid block. Add_noise injects random pixel noise to simulate rough textures. This allowed me to generate hard samples. I could create scratches so faint they were barely visible. If the model can catch those, it can catch anything. Now, let's talk about the brain of the operation. The Convolutional Neural Network, or CNN. To understand how this system works, you have to stop thinking like a human and start thinking like a matrix. When you or I look at a bottle, we see a distinct 3D object with transparency, reflections, and a shape. But when my code loads that image, it sees a three-dimensional spreadsheet. It's a grid of numbers, 150 pixels wide, 150 pixels tall, and 3 channels deep for red, green, and blue. That is 67,500 individual numbers. The job of the convolutional neural network, the CNN, is to find the pattern in those numbers that correlates with defect and ignore the patterns that correlate with reflection or a label. So, how does it actually see? It uses a mathematical operation called a convolution. Imagine a tiny window, let's say a 3x3 grid. We call this a kernel or a filter. Now, imagine sliding that tiny window across the large image, moving it 1 pixel at a time, from the top left to the bottom right. At every single stop, the filter asks a question. It multiplies its own values by the pixel values underneath it, and sums them up. If the pattern in the filter matches the pattern in the pixels, like a vertical edge where the bottle meets the white background, the result is a high number. The neuron fires. If the patterns don't match, the result is near 0. The neuron stays silent. In the very first layer of my network, specifically the SOMV2D, 32 block you see in the code, the filters are learning very basic things. They are basically acting like edge detectors. One filter might light up only when it sees a horizontal line. Another might light up when it sees a transition from white to blue. But a scratch isn't just a line. It's a complex texture. This is why we stack the layers. The output of the first layer becomes the input of the second layer. Now, the filters aren't looking at pixels anymore. They're looking at the patterns of edges found by the previous layer. This is where the hierarchy of vision begins. Layer 2 combines those simple lines to find corners and curves. Layer 3 combines those corners to find shapes, circles for bubbles, rectangles for the label. By the time we get to the deepest layers of my architecture, where I have 512 channels, the network is seeing highly abstract concepts. It's no longer seeing pixel 45 is gray. It's seeing there's a high-frequency jagged texture in the upper quadrant. That jagged texture is the scratch. But seeing isn't enough. We need to filter out the noise. That is why, after every convolution, I apply a ReLU function. Think of ReLU as a gatekeeper. It takes the output map and sets every negative value to 0. Why does that matter? In a digital image, black is 0. A negative value in a neural network essentially means the opposite of a feature. By zeroing those out, ReLU essentially turns off the lights in the parts of the image that aren't relevant. It forces the network to be sparse, to only carry forward the information that actually matters. It clears the fog, so the next layer has a clean signal to work with. I also apply batch normalization after every convolution. As data flows through the network, the values can drift. They might get really huge or really small. This makes the optimization unstable. Batch norm forces the data back to a standard scale with a mean of 0. It keeps the network centered. I also added a dropout layer with a 0.5 probability. This randomly turns off half the neurons during training. It forces the network to be redundant. It can't rely on just one neuron to say, this is a scratch. It has to build a robust consensus. Now, here's a specific design choice I made that differs from a lot of tutorials. At the end of the convolutional blocks, I used adaptive average pool 2D, 1. Usually, people flatten the data, which creates a massive vector and requires a specific input image size. If you change your image size, your model breaks. Adaptive pooling calculates the average of each feature map, condensing it down to a single one by 1 point, regardless of how big the input image was. This massively reduces the number of parameters and makes the model flexible. Finally, we have the classifier, self.fc equals nn, linear, 512, 1. It takes those 512 abstract features and boils them down to a single number. The most fascinating part of this process is that I didn't program these filters. I didn't write an if statement that says if pixel is gray, then scratch. When I initialize the model, all those filters are filled with random garbage numbers. The network starts out blind. It guesses randomly. But every time it guesses wrong during training, we calculate the error using the loss function. Then, using a process called backpropagation, we mathematically calculate exactly how much each specific number in those 3 by 3 filters contributed to the mistake. We nudge those numbers slightly. Maybe we increase a value by 0.001 or decrease another by 0.005. We do this millions of times across thousands of images. Over time, those random numbers evolve. They organize themselves into perfect edge detectors, perfect texture analyzers, and perfect shape recognizers. The network literally learns how to see the defects by minimizing the penalty of being wrong. To train this brain, I build a custom training loop in training_cnn.py. I use the atom optimizer. Unlike standard gradient descent, which just rolls down the hill of the loss function, atom has momentum. If it's moving fast in one direction, it keeps going, which helps it plow through noisy data and find the optimal solution faster. For the loss function, the way the model measures how wrong it is, I used BC with Logit's loss. This stands for binary cross entropy. I chose the with Logit's version because it combines the sigmoid activation and the loss calculation into one mathematical step. This prevents numerical overflow issues where the computer runs out of floating point precision when dealing with very confident predictions. I didn't just watch the accuracy. In anomaly detection, accuracy is a vanity metric. If I have 99 good bottles and 1 bad one, and I guess good for all of them, I have 99% accuracy, but I've failed my job. I track false negatives specifically. A false negative is a defective bottle that the model thinks is clean. That is the worst-case scenario. I also implemented a smart, early stopping system using a simple moving average. I tracked the loss over the last 5 epochs. If the loss started trending upward significantly, meaning the model was starting to memorize the images rather than understanding them, I cut the training cord immediately to save time and prevent overfitting. Once the model was trained, I moved to validation. But I didn't just want to score. I wanted to know why it failed. I wrote test_set_validation.py to be an interactive tool. It runs the model on the test set, but when it finds a mistake, it physically copies that image file into a specific misclassified folder. This feedback loop was critical. When I opened that folder, I saw a pattern. The model was consistently failing on bottles that had strong glare from the studio lights. The neural network thought the bright white reflection was a scratch. Because I could isolate those images, I could fix the problem. I took those specific glare-heavy images, ran them through my rotation augmentation script to create 500 variations of glare, and fed them back into the training set labeled as good. This taught the network, bright white spots are okay, dark thin lines are bad. This cycle, data engineering, augmentation, deep CNN architecture, and active validation, is what turned a rough prototype into a system capable of 98% accuracy. The code for this is actually quite compact, but the system thinking around it is what matters. I have the entire codebase here on my local machine, the synthetic generator, the training loop, and the CNN definition. I haven't put it online yet, but if you want to try building this yourself, or if you want to improve on my architecture, let me know in the comments. Would you like me to clean up the repo and upload it to Git? Thanks for sticking around for the deep dive. If you learned something about how industrial computer vision actually works, hit that like button. See you in the next one.